right? So here we go. Um, Getting to bases. Okay, we went over acids earlier. Acids were again going to be the pH for that is going to be 0 to 7. For acids, for bases, it's different. pH values for bases usually fall between 7 and 14. Okay, so again, electrolytes are going to be bases are going to be electrolytes, meaning that they can um, conduct a current. They taste bitter. They have an excess of hydrogen ions, which is OH ions in the solution. Acids had an excess of hydrogen ions. Okay, so this is different. So hydrogen hydroxide ions here for bases. They accept protons, and in acids we saw that they donated the proton, and they feel slippery. So they taste bitter. If you've had soap in your mouth, you know that it tastes kind of really bitter. Okay, it's not a very pleasing taste at all. Um, Also, they feel slippery on your skin. If you ever had bleach on your skin or Clorox on your skin, and especially soap, you know that it's very slippery. If you get bleach or Clorox on your hand, it's kind of hard to take that slippery off. Okay, it takes a while. Even if you run it underwater, your hands still feel pretty slippery. So these are the five. These are characteristics of bases here. Um, you should know them. You should know them fluently. Okay. All right, so bases again, pH is 7 to 14. These are household items that are usually uh, going to be bases. So we have ammonia, we have antacid, which is like Tums. Tums again is, you use that for heartburn, meaning that there's acid reflux coming from your stomach, and you take these acids to prevent it. Antacid, right? Without acid. Okay, so this creates a basic solution or a basic environment whenever you use these tums. Baking soda is also going to be a basic deal. It's going to be basic. It's going to have a base somewhere around probably like, I don't know, like probably like between 9 and 9.5, maybe. Let's see. This is going to be oven cleaner. Oven cleaner is very slippery as well. It does have some chemicals in it to take away the grease from your oven. Drano, also very slippery, can get past clogs. So that way, it can unclog your drain. So hair or gunk or grease or whatever it can get through that. And of course, you know that bars of soap are slippery. So bases are mostly going to be cleaners, okay? And remember these as the examples that are around your house, okay? All right, so in aqueous solutions, bases form hydroxide ions. So the hydroxide ions are going to be OH negative. We see here that this is going to be NH3. We mix that with water, and what happens is this H ion, okay, this hydrogen ion is going to be placed onto the NH3 on the other side of this reaction, right? On the other side of the arrow on the right side, which is the product side. You see how this H is now here, okay? And that an H has been taken off here. This is the hydroxide ion, okay? So this is what's happening when we're mixing a base with water. Okay, um, we create a hydroxide ion here. Okay, so that's what's happening here, and this is going to be an Arrhenius base. Okay, so this is going to be the definition of Arrhenius base. In aqueous solution, bases form hydroxide ions. Okay. So here, okay, here's the actual definition. Arrhenius base is a substance that increases the concentration of hydroxide. Okay, so remember this to be the definition for an Arrhenius base. You're going to need to know this later for your Nearpod assignment. Okay, so Bronsted and Lowry. Um, Basically, Bronsted-Lowry bases. This here is saying that the proton or the hydrogen is going to be an acceptor. Okay, it's going to be a proton acceptor. Okay, with acids, it was a proton donor. So what do we have here? We have a base here, NH3. We have, in this case, water's an acid, but it's just because um, the acid has the water has a lower pH than what the base is, because the base is between 7 and 14. The water is going to be neutral 7. So this is saying that this base here must be um, above 7. Okay. Usually 7 is going to be neutral. Okay. So anything higher than 7 would be considered a base. Water's usually considered neutral, but because this 7 uh, is the pH of the water, that means that this base must be a little higher uh, than 7. Okay, so we know this is base, this is the acid. Now remember that this H now goes on to this NH3 to create NH4 on the on the right side of the arrow, and it becomes its conjugate acid. Because this water molecule loses an H or a hydrogen proton, um, it is now considered a conjugate base. Okay, so again, when something loses, okay, when something like water loses a hydrogen, okay, and it's an acid, it becomes its conjugate base. The base on the other side of the arrow becomes the conjugate acid. All right, so give some examples here. Give the conjugate acid for each of the following bases. So here we have bromine, okay, and so in order for this to become a conjugate acid, we would have to add an H, okay. So Br, okay, we add the H. This is now going to be the conjugate acid of this base here, okay. Here we have one H, so if we add another one, see, 2, then it now becomes the conjugate acid of this base. Okay, so here you should realize that we have to add an H here, so then we have HCO3, and this is going to be the conjugate acid of this base right here. All right, so in chemistry, hydroxide is the common name for the diatomic anion OH, usually derived from the dissociation of a base. So again, same idea here, because this water molecule is losing this hydrogen to this base. Um, on the right side of the arrow, we have the hydroxide ion. All right, so again, identify the acid A, the base B, conjugate acid, and conjugate base. Okay, so here we have the hydrogen, the water molecule, which in this case is a base because the HNO3 is going to be the acid, meaning that it has a lower pH, so between 7 and 0, okay, than this water. All right. So because this water is going to gain this hydrogen from this acid, we now have H3O, which then becomes the conjugate acid, okay, of this base. HNO3 loses this H, and now we have NO3. So this acid here becomes the conjugate base on the right side of the arrow. Okay, again here, acid. Okay, this is the acid. This one's different than the top one. So now water is acid and is the acid in this case. The NH3 here is the base. This hydrogen will end up onto this molecule. And so on the right side of the arrow, we have NH4 because this gained the hydrogen, and this one lost the hydrogen. Okay, so oh, sorry. So this acid becomes the conjugate base here. This base becomes the conjugate acid. All right, so again here, the hydrogen is going to move on to there. The acid is going to give the base its hydrogen, NH4. So the acid, this acid becomes this conjugate base. All right, because it loses its hydrogen, and this becomes a conjugate acid. All right, of this base. So this base here, this acid gives its hydrogen to the water molecule, becoming hydronium H3O. So that becomes the conjugate acid. This acid loses its hydrogen and becomes its conjugate base. Okay. So amphoteric here can be an acid or a base, which is the H2O. All right, this last part here, acid and base indicators, are compounds whose colors change depends on the pH. Okay, so indicators are compounds whose colors change depending. Okay, so um, the colors change to help determine if a solution is acidic or basic. So we have stuff, indicators called litmus paper. If we have red litmus paper and we dip it in acid, it stays red. Okay, if we get red litmus paper and uh, dip it in a base, it becomes blue. All right, and vice versa. If we have blue litmus paper and dip it in an acid, it turns red. And if we have blue litmus paper and dip it into a base, it stays blue. Okay. Phenolphthalein is a liquid indicator. If we put drops of phenolphthalein in an acid, nothing happens. There's no color change. It stays clear. If we get phenolphthalein and we put some drops into a base, it turns pink. All right, so this is the end of this presentation, and you're going to use this to do your Nearpod activities. Get them in as fast as you can, and I hope you all have a wonderful weekend.